is Griffiths E&M section 7.1.1 Ohm's Law. So we talked about how current was really just a bunch of charges that move with some speed. Okay, so how do you get charges to move? Well, you have to apply a force. Okay? And that current density can then be written as something that is related to the force per unit charge, or the proportionality between how much force you apply or something applies and the amount of current that flows. That constant is the conductivity. Okay, so this is the current density. This is the force per charge, and this is the conductivity. Okay, if this is a material property, this is not the charge density. Okay, we're running out of Greek letters. This is the conductivity of the material. So you have some set of charges. A force generates a current by moving those charges. Particularly in the context of electromagnetism, the force that moves them is the electromagnetic force. Okay. We know that electromagnetic force, at least that we've defined in the past, was if a charge Q sits in a field, it is E plus V cross B. Right? So that means that the force per unit charge is just the thing that's in the parentheses. All right, so therefore, the current that you see is the conductivity times this product here. All right, well, it turns out that within a material that the charges are moving, while there is a current, the speed of all of those electrons is very small. Okay, so because these are very small, you can rewrite this as just the conductivity times the electric field. Okay. This is commonly referred to as Ohm's law. All right, let's go ahead and use Ohm's law. Got two examples that we can test out. Example 7.1. I have a cylindrical resistor. It is a length L. Each of these areas at the edges are A. It has some conductivity sigma, and there's a potential difference across this path of these two faces of V. All right. What current flows? Okay, so what current flows through this material? All right, well, we start by saying that the total current is related to the current density. All right, the current density is the amount of current that goes through a line or an area. That's J times A, because we have all the current going through our whole surface. But I know because of Ohm's law that J can be written as something related to the material itself, the conductivity times E. All right, that is this going from here to here. That's times A. All right, and then the potential difference can be used to rewrite the electric field. That's sigma times V over L times A. That's a physics, intro physics conversion right there. Therefore, I can rewrite the current as sigma A over L times V, or just inverting that expression, V is equal to I times L over sigma A. Great. That's the current that flows through that, right? And then rewrote it as this expression, which I'll explain for the reason why I did that in a second. Okay, example 7.2, slightly more advanced. I have two coaxial cylinders. So here is cylinder 1. Here is cylinder 2. This has a size of A. This has a size of B. Okay, the material in between these two cylinders has a conductivity of sigma. The difference between these two surfaces is a potential of V. What's the current that flows? All right. The total current is going to be related to how big our coaxial cylinder is. So let's say how much current flows per unit length L. Okay. So I'm going to assume here that the current density on the internal bit is the charge density rather is sigma. So the electric field within each of these, or within this cylinder, is lambda over 2 pi epsilon naught 1 over s in the s hat. So that's a consequence of Gauss's law, right? Okay. We're going to hold on to that. And then I know what the total current is going to be. And the total current is, we're actually going to do this now instead of just giving the answer like in the previous expression. That is going to be sigma E dot dA. All right, that's converted. Those two different bits of that equation are from Ohm's law. Sigma lambda 2 pi epsilon naught 1 over s times s d phi dz. S's cancel, and I'm left with my current is sigma lambda over epsilon naught times L, right, where my bounds went from 0 to 2 pi and 0 to L. Great. But that expression has sigma. Okay, I'm going to try to do something else to get rid of that so I can have a nice cleaner expression. The thing we haven't used so far is the fact that we have a potential difference across our two surfaces. So my potential difference can be written as minus E dot dl, or I'm going to go from the outer surface to the inner surface. That is minus lambda over 2 pi epsilon naught 1 over s ds from B to A. That becomes minus lambda over 2 pi epsilon naught natural log of A minus natural log of B. Combine those natural logs and that negative sign, and I'm left with that potential being equal to lambda over 2 pi epsilon naught natural log B over A. Okay, now both of these expressions have a lambda over epsilon naught in them. So I'm going to write lambda over epsilon naught is equal to I over L sigma. Okay, that's from this first expression. And then the second expression is also equal to lambda over epsilon naught. That is going to be, let's see, 2 pi v over natural log b over a. All right, that comes from this expression. I can then rewrite that what the current is equal to. That's 2 pi sigma L over natural log b over a times v. So I found the current that flows through this material with conductivity sigma. Okay. Again, I'm going to write this another way. I'm just going to invert it. V is equal to I times natural log of b over a over 2 pi sigma L. Now in both cases, I have found the current and then I've inverted it, and that gave me something that was the potential is equal to something with the current and some other proportionality factor. Right? This proportionality factor is the resistance. In intro physics, you probably talked about Ohm's law in terms of this, right? V is equal to IR. The potential difference is equal to the current times the resistance. There you have it.